Everyone, thank you for coming. So today I'd like to talk to you about this. Okay, now it's much clearer, right? So wait, the title of the talk is encrypted, so I just need to apply the decryption key. Okay, here we go. So, mastering cryptography fundamentals with Node's crypto module. That's a bit of a mouthful, so let's break it down. So first, what is cryptography? So I'm sure you've heard recently about crypto, but not in the context that you're probably thinking of. So crypto in Greek means hidden. And this is why cryptography is the study of or the science of techniques of secret communication or secret writing. Is there a problem? Yeah. Sorry. Thanks. That's better. So as you can imagine, having a way to communicate in secret and encrypt our correspondence plays a major role in today's online world. And because of that, it's a good thing that inside of Node.js, we have a built-in library for handling cryptographic operations and cryptographic algorithms. It's one of the built-in libraries, so you can just start using it right away. No need to install anything, just like the FS model, for example. And it's based on top of OpenSSL. So it's a JavaScript wrapper on top of OpenSSL, and that's an open source, widely used library that handles these cryptographic algorithms. Now, because it's one of the built-in modules, it has documentation up on the Node.js website, which means you can go and learn about what are the different APIs. But for me personally, when I became interested in this topic, I became a bit frustrated when I tried to use this as a resource, because what I realized is that the problem was really more with me, because this is a very flat alphabetical list of APIs, and it gives very little context about each algorithm. It kind of already assumes that you know what you're trying to do, what is the algorithm that is best for that use case, and then it just gives you the specific syntax in Node.js. So I had to go elsewhere and learn more about the fundamental concepts before this made any sense to me. Luckily, we have other great resources, some of them free online, to learn about the basics of cryptography. This is a book that I would really recommend if you're interested. So it's called The Code Book, and it talks about the history of cryptography, not just in modern computing, but going all the way back to Julius Caesar. And it's written in a very simple way to understand the concepts, and also it's very fascinating because it talks about the roles that these advancements in cryptography, how they played a role in the political and military struggles of the time. So you can understand how much of an impact this type of study or science has. And in fact, I find it kind of cool that today, on the 50-pound banknote in the UK, you have someone who is a cryptographer, a cryptography researcher. This is Alan Turing, who played a major role in breaking the Enigma machine encryption. And so obviously he did amazing things, but I kind of like to think that it's pretty cool because in a way he is a programmer just like one of us. So I'm imagining somebody going to build stuff, and then 40 years later they put his face on the money. That's pretty cool. So what I want to do in this talk today is to kind of give you a shortcut through the path that I took. So to learn and cover the basic concepts that we have in cryptography, to understand them at the theoretical level, but then to make sure that we're covered in a practical way to actually get started, we're going to see how we actually do things in code with the crypto module. So let's dive in. My name is Yonatan Mevorach. I work at Wix. This is where you can find me online. So the first thing that comes to mind when we talk about cryptography is this idea of encryption. Encryption is what lets two parties communicate over an insecure channel, something where they take under consideration that somebody might read their correspondence, and because the message is encrypted, they don't have to worry about that party to kind of understand the original message that they're hiding with the encryption process. So when we typically talk about cryptography, we use this couple as an example, Alice and Bob. Now, unfortunately, we also have Eve, who is here to represent a potential hacker or malicious actor. And when Alice and Bob communicate, they're going to have to assume that Eve is there eavesdropping. Now, Alice and Bob came to build stuff today. Luckily, Eve is nowhere to be seen. Shit, okay, she's here. So we have to watch out and we have to apply encryption very carefully. All right, so for this first type of encryption that we're going to show, Alice and Bob need to have something which we call the shared key. And this is a value that they both know. They both need to use the same value, which means they also have to agree on which value to use as the shared key. And it's important that Eve will not have access to this value, because if she does, she'll be able to perform the decryption. So, and we're going to talk a bit later about how we decide exactly on what the key is. So let's start with a mental model of how the encryption works and get familiar with the basic terms. So to apply the encryption algorithm, Alice takes the plaintext and the key. The plaintext is the original message, and she passes it through the deterministic encryption algorithm, and what she will get is the ciphertext. So for example, if this is the message, then the ciphertext will look like this, something which looks meaningless. And this is why even if she sends it over an insecure channel over some network that she can't trust, and Eve is there to read the message, nothing bad happens. And then we have Bob, who is able to apply the decryption in order to read the original message. So when we do this in real life, there are a couple of more things that we need to be aware of. And the first thing is which encryption algorithm do we choose, because we have many. And overall, they all work by performing a set of substitutions and transformation on the original plaintext to derive the ciphertext. So this is the first bit of code from the crypto model that I want to show today. And this is the getCiphers function. And as the name suggests, this returns a list of ciphers or cryptographic algorithms that are available for you to use. So when I run this on my machine, this returns 171 different algorithms. So you have many options. And the one that we're going to take a look at in this example is part of a family of protocols or algorithms, which is called Advanced Encryption Standard. And as the name suggests, it's a standard, so it's widely used and it's implemented in different languages. So that means that you can do the encryption in Node.js and somebody could do the decryption in Python or .NET or any other language. And it's considered advanced enough, so it's still relevant today. We have other algorithms that, because of the increase in computer power, are considered outdated today. So this is still relevant. Now specifically, we're going to take a look at AES 256. This stands for the size of the key. So we want to choose a key that's from a range that's big enough so that if somebody like Eve is trying to guess the key, they will have to if they're trying to guess the key by brute forcing and trying all different combinations of the key, they will take them a really long time to do. So 256 in this context means that the size of the key that we're going to use is 256 bits. And CBC stands for cipher block chaining. And this is a mode of encryption where we split the original plaintext message into these blocks, and then we encrypt each one separately. Now, in order to compute the very first block, we need to supply something extra, which is called an initialization vector. So let's talk about what value we use as the initialization vector and why we have it in the first place. How is it making the encryption more secure? So this is the revised encryption process. It's exactly as before, but now we have to pass in the IV as well. So the value that we use as the IV is a random value. That means that even if every morning when Alice wakes up, she sends Bob the same message, hello, which means the message will be the same and the key will be the same, she will still use a different IV value every time. And because the encryption algorithm is deterministic, this means that the resulting ciphertext will be different every time. And this is why it's making our encryption more secure, because it's preventing an attacker like Eve to try to guess our plaintext and find patterns and relationship between the original plaintext and the resulting ciphertext, and that way to try to guess the key. So this is from Alice's point of view, and then she sends Bob the IV, the ciphertext, and the algorithm, or they can just choose to use the same algorithm every day, and then it won't need to be part of the message. But at any rate, now that Bob has this, he can apply the decryption using the same IV value that Alice used. So let's see how this is done in code. So this is first Alice's encryption logic. So we have the algorithm, like we said. This is the name of the algorithm. The plaintext is not used as a string. It's converted into a buffer. We never use strings directly when we're doing cryptography. Then we have the random value generated for the IV using the random bytes function. Then Alice loads the key into memory. We'll talk later about how exactly we decide on what the key is. And then she creates a cipher object using create cipher IV, passing in the algorithm, the key, and the IV. And then to compose the actual ciphertext, she calls cipher.update, passing in the plaintext. You can call this many times if your plaintext is very big and you're composing it over time. And when she's done, she calls cipher.final, and this gives the resulting ciphertext. Now to perform the decryption, notice how much similar looking. It's like the mirror image of the encryption logic that Bob uses. So he gets the IV, the ciphertext, and the algorithm. He loads the key into memory, and then he calls create decipher IV, decipher being the opposite of cipher. And then, again, very similar looking API, calling the update method on the decipher object, and this gives the original plaintext back. Now, we kept it pretty vague so far what value we use as the key. Now, Alice and Bob might be tempted to use a human memorable password that's easy to remember as the key itself. But this will be a mistake. Why is this? This is because we mentioned before that we purposefully use a wide range for the size of our key, so that if the attacker, if she's trying to guess the key, she'll have to try a very large set of options. If Eve can assume that Alice and Bob are using a human memorable password as the key, then Eve will be able to try a much narrower set. And it won't even help if we're trying to be clever as users by replacing like O's with zeros. This still leaves a very, very narrow set of options to use. So we don't want to use the password as the key itself. But what can we do if we still want to base our security about something that we remember? So one of the options to use is something called a key derivation function, or KDF for short. And as the name suggests, this is something that lets us derive a strong, long key from something else. For example, a password that we remember. Okay? So this works like very similar to a hash function, if you're familiar with them, to check like the integrity of the checksum of some file. But interestingly, unlike a normal hash function, or unlike most functions, a KDF is actually designed to be slow on purpose. It's meant to be CPU heavy and also memory heavy. Why is this? We're making this function slow on purpose so that if Eve is trying to take, again, a list of common passwords, let's say she finds it online, and she's trying to loop through them and compute the resulting key using some well-known KDF, it will be very slow for her to do and make it not worth her while. So problem solved, right? But if you think about it, if Eve is smart, what she can do is she can go online and not just download the list of the 10,000 most used passwords, but also find their value when passed through some well-known KDF and use a pre-computed list that somebody else has already taken the time to run this costly function many times. So if this was the actual behavior of the KDF, then the KDF is not making our correspondence any more secure, and it's just making the process more complex. This is why in real KDFs we have another crucial parameter, which is called the salt. And again, what we pass to the salt is a random value. So this means now that Eve, even if she gets a hold of our salt, and she's trying to guess our password using a list of common passwords, she will still need to run this process of taking the password that she's trying to guess, our unique salt, combining them, running this very slow function just to get these keys that she wants to try. And hopefully this will make her just give up on the entire process. So those are KDFs. Let's see how this looks in code. So very similar to the process we showed before, I'm highlighting only the parts that changed. One of the KDFs that's built into the crypto module is a KDF which is very popular, which is called script or secure crypt. And basically, you can see here the two parameters that we discussed, the password and the salt, where we generate with random bytes. And you pass them to script and you get a key that you can later use. Other notable mentions here, we have two other KDFs baked into the crypto model, HKDF and PBKDF2. That's a bit of a long name. All right. So as we saw so far, being able to generate random values is super critical to getting cryptography right. So let's see how we can generate random values. So the first rule of doing that is not to use math.random, which you're probably familiar with if you're working with JavaScript for a long time, because as the MDN doc state, it is not considered cryptographically secure, which means that an attacker can either guess what this will return on your machine, or they can make you think that you're generating something random, and in fact, this is something that was planted there by the attacker. So it's not what you want to use. So what can you use instead? So inside the crypto module, we have several ways of generating random values. All of these are asynchronous, but they use a callback style, which is kind of not popular these days. So if you want to use them as promises, you need to call util.promisify on them. So the first one is the one we showed before, random bytes. You give it the size that you want, and it returns a new buffer of that size with random values inside. The other one is random fill. This takes an existing buffer and either replaces all of it or a subset of it with random values. You have random int. Given a minimum and maximum range, it returns an integer in that range with a random value. And you have random UUID. So the encryption process that we showed so far, its security really hinges on the fact that Alice and Bob have this shared key that they both know and only they know and no one else. So this means that they have to exchange it in a way that's offline. So this was nice maybe tens or hundreds of years ago when two parties would meet, decide on the key, and then go their separate ways and exchange physical like letters. But I hope that you realize by now that Alice and Bob represent computers. So this is not really relevant for computer use, right? And in the internet and networks. We have different computers on the other side of the world. They don't have an easy way to meet offline in a coffee shop and decide on a cute shared key that they will use. So what can we do? So this is something that Alice thought long and hard about. And honestly, this is something that I thought long and hard about as well. And this was something that a lot of smart people thought about for a long time, and this became known as the key distribution problem. Now, luckily, just in time for when the internet was taking off, a group of scientists in the 1970s in the US came up with an elegant solution to the key distribution problem. So let's see how this algorithm works. The algorithm is known after the creators. This is the Diffie-Hellman key exchange. So let's see how this works. In order for Alice and Bob to generate a shared key, even though they're communicating over an insecure channel, and end up with a shared key that only they will know, this is the steps they will take. So Alice will get a prime, a generator, and her private key, and she will use them to derive her public key. Then she will send these over to Bob. Bob will do the same with the same prime and generator, but with his private key, which will generate his public key. Then he will take Alice's public key and use them to derive the shared key. Then we need to go back and forth, right? This is a key exchange. He will send his public key back to Alice, and then she can derive the shared key as well. I know this looks like very like random values and stuff. It's not really important what exactly each box represents, but I just want you to, the main thing I want you to take away is what they both end up with. And that is that even though they communicated completely in the open and they're taking into consideration the fact that Eve was reading all of the messages that they sent back and forth, Eve has no way to come up with a number in purple, and Alice and Bob both do have this identical value. So this is why this was a very groundbreaking achievement. Let's see how this is done in code. To do the key exchange, this is Alice's code. First she calls create Diffie-Hellman. This on my machine takes 20 seconds, so it's a very slow function to execute. And then she gets the prime, the generator, and her public key. The private key is is hidden inside. And then she can send these over to Bob. Bob gets these things. He calls create Diffie-Hellman. Because he's using an existing prime and generator, this is much faster this time. He gets his public key, and he can also already compute the shared key. And then on Alice's side, she can compute the same shared key. And then they can start encrypting using this key in the same process we showed earlier. Another notable mention here is something called elliptical curve Diffie-Hellman, also a product of this same group of researchers and something that's widely used today. So you can read about it more in the docs. So, like I said, this was a groundbreaking achievement, but if you think about it, we still have some disadvantages, right? Because we still have to perform this like dance of the key exchange with each party that we want to communicate with, and that's kind of a shame. So now we're going to take a look at, also in the 1970s, also a group of researchers from the US who came up with a different solution to the key distribution problem, which even solves these disadvantages of the Diffie-Hellman key exchange. And the algorithm that they come up with is known after their initials, RSA. So now, really, there's no need to do any key exchange, and we're going to understand why. So the first thing that Bob has to do is get two numbers, one can be derived from the other, a private and public key. And then he makes this key known to the world. This is another advantage of RSA versus the Diffie-Hellman key exchange, where with the Diffie-Hellman key exchange, you have to do this key exchange with every party that you want to communicate with. And here, he makes this public key known to everyone, and anyone can use it to start encrypting and sending Bob messages. So if Alice wants to send Bob an encrypted message, she takes Bob's public key, the plain text message, and from these, she can derive the ciphertext. And then the ciphertext is sent to Bob, and using his private key, he can do the reverse decryption. So because we have now a different key, one for encryption and one for decryption, this is how we completely avoid the key distribution problem. And of course, it sounds very simple when I say it, but the trick was to find, the math that makes this work, which you can read more about in the book if you're interested. So now that we have this process, this really makes our lives much easier. So let's see how this is done with code. In code. So this is first how to generate the keys. Bob needs to do this, like I said, only once, not just for communication with Alice. So he calls generate key pair, which generates for an RSA key pair, and this generates the two keys. And then he can save them to file, the public key in order to share with others, the private key to store in some secure drive. And this is how you export these keys to a file. Now, in order to perform the encryption using this, what we call asymmetric encryption, because we have different keys for encryption and decryption, this is how Alice does it. So she reads Bob's public key into memory. She takes the plaintext message as a buffer, and she calls public encrypt, and this will give her the ciphertext. She needs to pass the public key, the plaintext, and a configuration value, which is called the padding. And then to perform the decryption, so Bob gets the ciphertext, uses his private key, and calls private decrypt in order to perform the decryption, passing in the same parameters, the key, the ciphertext, and the same padding value, and this will give back the original plaintext. Something that you need to be aware of, pretty recent stuff, is that RSA is beginning to show its age. And we have researchers who, using a quantum computer, say that they were able to break RSA encryption. I don't think this is something that you need to worry about. This is for the people working on very cutting-edge stuff. Even if somebody has some entity, has this capability, they're not going to waste it, quote unquote, on the simple things that are in the commercial space. But it is something to be aware of. And I think I did read that Apple, in iMessage, they're already using a type of encryption that they were able to prove that can be protected against being cracked by quantum computers, even though they're not that widely available. So now it's time to think, have we solved all of the problems in the cryptography space, or are there any problems still left? Well, now every person, every entity on this network has their private and public key, and they can send messages back across. But what we don't have yet is a way to know that the message that we got from a certain entity really came from that entity. And that plays a major role, right? When we get a message, we want to make sure that we trust that it really came from who we think it came from. So this is where we get into the world of signing and verifying. So for the sake of this example, let's say that Alice is one of the organizers of Build Stuff, and she wants to send Bob a message saying that he can go to the conference. So obviously Bob needs to be able to prove to himself and anyone else that the message really came from Alice. So let's see how this is done. For the sake of this example, the message itself is not encrypted, but it can be. So what we do is, what Alice does is she takes her private key and the message, and she creates a signature, which looks like again like a value of if you pass it through like a hash function, it looks like just a random value. But the signature is the key thing that's going to make it so that Bob can verify that the message really came from Alice. So her public key is known to everyone, and she sends Bob the message and the signature. It's fine if other people read this message as well. And then Bob, to be able to prove to himself or to anyone else, he can take Alice's public key, the message and the signature, and run it through this cryptographic verification process and see if this returns that the signature is valid or invalid. Now the main thing here is that only someone with access to Alice's private key, which we hope is Alice, can create such a signature that when combined with Alice's public key will come out as something that's verifiable. So let's see how this is done in code. In order to create the signature, Alice reads her private key into memory. She takes the original message and she calls crypto.sign. And she needs to pass in the hash function to use as part of the signing process, the message, and the private key. And then Bob can perform the verification. He reads Alice's public key into memory, and he calls crypto.verify, and this will return a boolean of true or not. He needs to pass in the same parameters, which hash function to use, the message, the Alice's public key, and the signature itself. And this returns true if all of the math and the cryptography all line up. Another notable mention here, we have something called create HMAC, which stands for a hash-based message authentication code. And this goes to the world of signing in the world of symmetric cryptography, when we don't have a different keys. And it's something that's quite popular today. You can also read more about it. All right, so now I want to take a slight detour and talk about when do we ever get to use this stuff? Because this is like the basis of HTTPS and SSL. When do we get to roll up our sleeves and build something interesting with cryptography? So this is one example. I'm not sure how it was here in Lithuania, but 3 years ago, where I'm from, if I wanted to go to a coffee shop, I had to do this fake dance with the host, where I would show him the QR code that proves that I was vaccinated. Now, it was a complete joke because they never bothered to scan the QR code, so I could have just printed a QR code that leads to a Rickroll video. But at least in theory, somebody thought about an elegant solution there, because what these QR codes that we got, what they contained, is a standard by the EU, which contained not an encrypted, but a plain text JSON value, which has your name, what vaccine you got, and when you got it, and a signature to make sure that it's legitimate. Now, the signature was created with the private key of the Ministry of Health, and the public key was actually available for everyone on GitHub. So either you could use their application and scan the code, or you could create an app yourself that works completely offline, no internet necessary, that can read the message, which is the JSON details of when you were vaccinated, get the signature, and validate it using the public key. So I think kind of an interesting usage of this type of technology. So again, I'm asking the question, are we done? Did we solve all of the problems in cryptography? Can we trust everyone on the internet now? Well, I want you to think about the process I showed for signing and verifying. And if you think about it, it didn't really prove what we said it would, because I said this will allow us to prove that the message really came from Alice. But all it did is make us, it helped us prove that the message came from some entity, somebody posting online that says, I'm Alice, and this is my public key, and this is how you can verify that message came from me. But really, now the weakness in our system becomes, how do we know that a specific public key really does belong to a certain person or entity? So this is where we get into the world of certificates or public key certificates, because they help establish ownership and prove ownership of certificates in general. So before we dive in, I just want us to cover what we talk about when we talk about certificates in general. Okay, so this is a certificate, not a cryptographic one, right? So this was a certificate that I got, and let's go through the parts. So it has who was it to? Okay, this is my name, so this is who it was issued to. We have some claim that the certificate is giving us, and that the person who gets the certificate, me, is the absolute best at remembering Git commands without ever needing to consult documentation. And this was given to me by someone. This is by the creator of Git. And you can tell it's legitimate because we have this signature, right? So these are the 4 parts that we have in a certificate. Who is it for? What does it say about that person? Who is the person giving that, making that claim, the person who issued the certificate? And we have the signature. Now, did I really get a certificate from the creator of Git for being the absolute Git master? I'll let you decide. But whether or not you trust this signature, luckily in cryptographic digital certificates, we don't have to trust anyone or apply this judgment. We can actually verify the signature. So this is why this process is a lot more effective and we can trust it. So what I like about this, though, is that now if Bob wants to start communicating with Alice and he wants to know that the message really came from Alice, really there's no magic solution. There's no like new algorithm that solves this problem. It goes back to the very simple concept of, in order to trust someone new, I need to trust some other party that we both know. So this is Carol. I hope you can tell by the clothes that this is Bob's sister. And she's also a friend of Alice. And she's going to help establish this initial trust between Alice and Bob. So what Alice now wants to do is create a certificate that proves that she is the owner of some public key that she posts on the internet for everyone to start communicating with her. So in order to create the certificate, what she will do is she will take the public key, the main thing that she wants to establish ownership of, add some metadata about herself, what's her name, what country she's from, etc. And she will create something which is called a certificate signing request. And this is the part of the certificate which is to be signed, TBS, to be signed, but it needs to be signed by someone. And that person that's going to be signed by is the other entity that wants to help out Alice and kind of use her reputation in order to help out Alice so that people that trust Carol will trust Alice as well. So Carol, if she's willing to help, she takes the certificate signing request, she takes the TBS, the to be signed data, and she signs it with her private key. And then Alice creates a certificate using the signature that she got from Carol. And then she makes this available to the world, and then anybody who already trusts Carol can go and take Carol's public key and Alice's certificate and make sure, using the same verification process that we showed before, that the signature really does match, along with the metadata and everything else, to Carol's public key. And this lets Bob, in this case, know that if he trusts Carol, then he can trust that this is really Alice's certificate, and therefore he can trust Alice as well. So let's see how this is done in code. So to read a certificate into memory, we have the X509 certificate class. This is the name of the specification for how to structure certificates. So we read the certificate into file and parse it this way. Then we can read a metadata on the certificate. What is the subject of the certificate? Who was it given to? CN stands for common name, so common name Alice. We have the issuer, in this case Carol. We can see valid from to valid to. What is the date range that the certificate should be considered trustworthy? And then to perform the verification, what Bob can do is he can read Carol's certificate in the same way. Carol's certificate contains Carol's public key. And then Carol's public key can be used to verify Alice's certificate. And if this returns true if everything lines up. So again, I'm asking you, are we done? Are there no more problems left? Well, if you're very skeptical, and I hope you are, you should be in the world of cryptography. How can Bob trust his sister, Carol? Well, how do you begin to trust your sister? You have your mom. And if you trust your mom, she tells you to trust your sister. So what I'm trying to illustrate here, and you can see this if you go in your browser and take a look at the certificate, which you can do, is you have something which we call a certificate chain or a certificate hierarchy. And when you go to a website, you download some certificate, you want to verify it, you need some other certificate that you don't have, so you go get that one. And at the very top, you reach your mom certificate or your root certificate, which is a certificate that you just have to trust because it's baked into your operating system and not because you download some other certificate. All right, so we've covered these concepts. We have, encryption, KDFs, randomness, the asymmetric encryption, or the key or solutions to the key distribution problem, and the world of signing, verifying, and certificates. Another notable mention, if you're doing JavaScript but not in Node.js and rather in the browser, you have something which is called the Web Crypto API, which the APIs look different from what I've showed, but it covers the same, the same algorithms. So you can learn more about that as well. Here you can find all of the code from the talk today. And because it's cryptography and we don't trust anyone, it's covered by unit tests, so you can run them to make sure that it's actually working. So don't trust anyone. This is where you can find me online. I have a big blog post which talks about this cryptography in Node.js, which you can read, and also some other projects. This was also during COVID. I was very bored alone in my room, so I took apart an arcade machine and I made it show Grafana graphs instead. You can read more about that. And thank you for listening. If you have any other questions, you can ask Alice and Bob later. Thank you.